Hello, everyone. This is the fourth in a series of lectures covering Chapter 35. Today we'll be talking about refraction. So, refraction happens due to the transition of light waves onto a new medium. We've already seen that an incident wave coming through a one-dimensional medium, so just kind of like a traveling pulse on a string, can transfer onto a thicker or even smaller string, and in doing so, you have this transferred wave. Some of the energy transfers, and the properties of this transferred pulse are a little bit different from the incident one due to the different properties of the medium. And depending on whether the medium's thicker or thinner than the incident one, you'll get a reflected pulse that's either upside down or the same side going back through the original medium. So with light, the same thing happens where some of it gets reflected, some of it transfers into a new medium. And what's interesting about light is that since it's three-dimensional, the first part that enters a new medium of the light wave will sort of interact with the particles first, and then the remainder of the light wave will then enter with a little bit of a delay. So it's kind of like a barrel rolling off concrete and hitting a patch of grass at an angle. So the first edge of the barrel that hits the grass will slow down, while the bit of the barrel that's still rolling on the concrete will still be rolling at its initial speed. And so the barrel will tilt a bit towards the grass, and then eventually all of it will transfer into the grass. What this means is that the way the light is angled when it transfers to a new medium will change. So to restate, two things happen when light encounters a boundary between mediums. So, like in the drawing here, we have light ray, an incident light ray, reaching the interface between air and glass, and some of that light wave, some of that energy will get reflected, and we know the reflected angle can be predicted with the law of reflection, but also some light will enter the new medium. And you might note that when it enters a new medium, we draw that transmitted ray as the refracted ray, and there's this angle here, theta 2, that you measure from the normal, that in fact won't be the same as theta 1. Much like the barrel going from concrete to grass, light will tilt away. Sorry, in this case, light will tilt towards the normal as it enters the glass. In fact, what could happen too is that depending on the two mediums, the light can also bend away from the normal. So if you had the light rays coming from water onto air, then the refracted ray that passes through the water-air boundary into the air will actually be refracted away from the normal. So the actual angle of refraction, which we write as theta 2, depends on the ratio of the speeds of light in the two mediums that make up the interface. So the faster the refracting medium is, which in this drawing will be glass, the faster light moves in that medium, the smaller the refracted angle. In this case, light moves slower in glass and air, so the ratio of V2 over V1 would be less than 1 since it moves faster in air, which would mean that if you see that's equal to the ratio of the sine of each of the refracted angle over the incident angle, would mean that the refracted angle is effectively smaller than the incident angle. So in this quiz, we have this beam on the left hitting the surface, and we're asked to find which of these are reflected and which ones are refracted. So reflected beams are those that stay in the same medium. So that would be beam number 2 and beam number 4, because beam number 4 is reflecting off beam number 3, so they're both in the same glass plate. The refracted beams are the ones that pass on to another medium. So beam 1 in air passes on to the ray number 3. And you can see then, right, like if you were to grab a ruler and place it alongside beam 1, you'd see that beam number 3 is angled away from that ruler, right? That's refraction in effect. Light slows down in the glass, so the angle it makes with the normal is smaller than the angle it makes the incident angle in air. And the last refraction happens when the light ray 4 passes from the glass plate back onto air, and you can note that light ray 5, the refracted ray, is bent away from the normal in this case. Since light moves faster in air, its angle is bigger. Note that we said the speed of light in a vacuum is 3 times 10 to the 8 meters per second. It's really fast, and the instantaneous speed of light is always that. It's just that in most mediums like glass or water, well, what happens with the light beam is that the light waves end up having these interactions with all these particles in the medium, and as such, it takes a bit longer for light to get across the medium. It does, however, keep all its energy as it crosses the medium, right? So it's just that due to interactions, it's a little bit moving all over the place, but still progressing through the medium. So the average speed then in crossing the medium is slower than if it were just crossing air or crossing, a vacuum. So here we go. That's the answer. And the fun thing is that refraction rays are effectively reversible, which means that you can have the incident ray become the refracted ray, and the refracted ray become the incident ray, and the angles would still be the same. So in the drawing here, had the ray had been coming from the glass, originating in line B towards the glass air boundary, then you would have the light refract and become ray A, moving up and to the left. So the incident ray would be, again, below the surface in glass, would be on the right, pointing up and to the left. The refracted ray will be in air, away from the normal, more farther away from the normal than the incident ray. And there will actually be, you won't see this reflected ray here in the drawing. That's the light beam reflecting off the glass. You will see a reflected ray, right, that stays in the glass. So you'd see the incident ray at point B coming into the glass air surface, and then you see a reflected ray pointing downwards and to the left on the other side of the normal inside the glass. So you could just then flip the arrows of the incident and refracted ray, and all the angles would still be true. So again, just to restate, the idea is that when light moves from a material where it moves faster to one where it moves slower, the angle of refraction is slower than the angle of incidence. Light moves towards the normal. That's why if you stick a straw in a glass of water, or your favorite soda, you can kind of look down at the glass and you'll see that the straw seems to be bent inwards below the water. So in this example then, right, you see how light beam tracks air, and sorry, a light beam strikes a surface of glass, and some of the light, you can assume that reflection always happens, but for simplicity, we're just showing you the refraction. Some light refracts into air, into the glass, I mean. So it's going to bend towards normal. And in the second case, you see a beam coming in the glass, refracting out into the air below, and in this case, light bends away from the normal. So, speed of light in any material, since there's always some matter there, the speed of light's going to be slowed down by that matter. And then that means that overall, the speed of light through any material is less than the speed of light in a vacuum. Light travels at its maximum speed, c 3 times 10 to the 8 in a vacuum, and anywhere else in any actual medium, it's a bit slower than that. So it's good to, rather than just talking about the speed of light in any medium, we can instead talk about the index of refraction of that medium, which we indicate using the letter n. And that's just defined as the ratio of the speed of light in a vacuum to the speed of light in the medium. So that means then for the vacuum, the index of refraction is equal to 1. And for many different substances like air or like carbon dioxide, very, very sparse gases, the index of refraction is almost 1. It's really close to a vacuum. So it's a good number that gives you an idea of how fast light in the medium goes as compared to the vacuum, right? So it kind of standardizes the different speeds of light in different mediums with respect to the absolute max speed. Also note that it's a ratio of speeds, and it's dimensionless then. And also, since the speed of light in a medium is always slower than that of light, you can expect n to always be bigger than 1. So just to list here a few substances, a few solids or liquids, going to see how the index of refraction is, which again, a bigger index of refraction tells you that light moves slow through them. So something like gallium phosphide with an index of refraction of 3.5, that tells you that the speed of light in this phosphide is many times slower than that in a vacuum, so that you can expect a big difference between the angle of refraction and the angle of incidence. Though, if you look on the lower right, like I said, the index of refraction is pretty close to 1 for air. So we approximate the index of refraction in air to just be 1, like in a vacuum, for most problem solving. So it's worth pointing out that for light, its frequency is actually tied to its energy. So when light travels from one medium to another, its frequency does not change. So the transferred light waves retain the same frequency through one medium to the other. And again, right, this is related to energy. Like, that's why the frequency has to stay the same, because if not, then you will have this pileup of energy on one side. If the frequency was bigger, medium, in the first medium and the other, and there's no mechanism for energy just randomly dissipating at the boundary. So it must be constant as light passes through a boundary. That being said, though, the waves do slow down or speed up as they pass to another medium, and light waves do follow the wave equation we've seen, that speed of the wave is equal to its wavelength times frequency. So if the frequency remains constant as it passes through the mediums, but the speed of the light waves change, then so must the wavelength. The speed and wavelength are proportional, so the frequency being constant means that in a slower medium, the wavelength decreases, and in a faster medium, the wavelength increases. Now, it can be shown using a principle that we'll talk about in this chapter that, well, if you can talk about the ratio of the sine of the incident and refracted angles in terms of the speeds in the mediums, you can also talk about them as just ratios of the indices of refraction for each medium. And this is actually Snell's law in its title. And what that tells you, right? It's again, it's a summary of what we talked about, where the medium with a smaller index of refraction will have a if we come from a small index of refraction to a bigger index of refraction, such as air to water or glass or sodium phosphide or carbon, then light's gonna bend towards the normal. If you're going from a bigger index of refraction to a smaller one, so from a slow to faster medium, then the light's going to bend, it's going to refract away from the normal. And by the way, in the drawing, you can actually see that you're moving to slow medium. So that's why the wavelength shortens in this medium number B. So quick quiz here. We're passing from index of refraction of 1.3 to 1 of 1.2. And what can we say about the refracted ray? So we're moving to a lower index of refraction, which means that light moves faster there. And so light's going to bend away from the normal. So this could be the same thing that happens if light moves from water to air or glass to air or anything like that. Anyways, I think that's almost all we have to talk for this section. There's one more thing to show, which is the prism, which is just taking advantage of refraction to redirect light. And in the case of a prism, where you basically have a triangular lens, that'll mean that the incoming ray will refract twice, and it'll deviate by some amount equal to the combined refraction, both when it enters the prism and when it leaves the prism. So there's a few things you can measure. First one being the angle of deviation, which is the total angular displacement of the outgoing ray compared to the original ray. You can kind of see the angle there, delta, on the right side of the triangle. There's also the apex angle, which is just the angle between the sides of the prism where light enters and leaves. So in this case, right, it's a equilateral triangle, so the apex angle would then be 60 degrees. But prisms can take many shapes, so whatever side of that shape light enters and whatever side light leaves, the angle between the sides is what determines the apex angle. In this case, it's fairly obvious due to the easy geometry of a triangular prism. Anyways, that's all for now. Please join me next time as we talk about the Huygens principle.